Alright, so today I'm going to be explaining this paper with the title GraphGDP, Generative Diffusion Processes for Permutation Invariant Graph Generation. This IEEE paper in 2022. Graph generative models have broad applications in biology, chemistry, and social science. However, modeling and understanding the generative process of graphs is challenging due to the discrete and high-dimensional nature of graph, as well as permutation invariance to node orderings in underlying graph distributions. Current leading autoregressive models fail to capture the permutation invariance nature of graphs for their reliance on generation ordering and have high time complexity. So we propose a continuous time generative diffusion process for permutation invariant graph generation to mitigate these issues. We first construct a forward diffusion process defined by a stochastic differential equation which smoothly converts graphs within complex distribution to random graphs that follow a known edge probability. Solving the corresponding reverse time SD, graphs can be generated from newly sampled random graphs. To facilitate the reverse time SD, we newly designed a position-enhanced graph score network, capturing the evolving structure and position information from perturbed graphs for permutation equivariance score estimation. So we have this position-enhanced graph score network. So we perturb the graph data to random graphs with an underlying simple edge distribution. Can be achieved by a continuous time forward diffusion process, so which is described by this SD here. So we can convert this SD with the score of data distribution, and a graph sample can be transformed from a newly sampled random graph via generative random process. The lower triangular part of adjacency matrices perturbed from the same graph at different times are shown in the first row, and the corresponding discrete graphs are below them. So this is just the adjacency matrix. No information from node types. Just if there is an edge, if the edge exists or not. So from denoising score matching, I have a playlist for denoising score matching. Then I explain in that the objective is modified for score training. Now we are learning this score. This score, we want to learn it using this neural network F theta as parameter theta that we can learn it. Note that this transition kernel that you see, this one keeps a tractable Gaussian distribution. So that's why we can compute it. If it is not simple, then we can use kernel density estimation to just approximate it. First we simulate the process, and then we estimate it. So in any case, we can estimate it. So you see the illustration of the objective computation for the proposed graph score network. You uniformly sample T, compute perturbed graphs and the gradient of log probability density, and then train graph score network to estimate the scores. So our goal is to construct a diffusion process that perturbs graphs toward the equilibrium state like equation 1. So a sub t, which is indexed by a continuous time variable, we denote a0, we draw it from our original data p0 distribution. So it's just an adjacency matrix drawn from original data. Also, we can draw from the final perturbed adjacency matrix. The choice of the drift function and the diffusion coefficient is indispensable for success of diffusion process. So assume that your beta is just, we have just a linear scaling function. So our beta is linear. So our STE is here, and we can see that with the affine drift coefficient, the perturbation kernels are Gaussian distributions. So because of this simple form, we have this Gaussian distribution. It's so easy to derive this normal distribution for AT for this mean and this variance. So with these perturbation kernels, we can perturb the graphs and compute the score target efficiently at any time without running the forward diffusion process step by step. So with the defined forward process, including both continuous and discrete states, we build up the training procedure like this. So we learn it. A graph score network learns to estimate the score of graphs with varying perturbation degrees. We first extract appropriate node features and edge features. Of course, they use this random walk in order to have R-step random walk, to have node position features. And from that, they obtain shortest path distance between node I and j. So the initial edge features is just the concatenated of with E, shortest path distance. And the rest of that is just doing message passing, and everything is very simple. Here we have edge features, and then after training the time-dependent graph score network, we construct the generative diffusion process by the reverse time STE. Because we have learned P, because we have learned this score, then we can simulate it. Our simulation is very simple because we use Euler-Maruyama method. It's just a discretization of ST, nothing important. Langevin MCMC like score-based models, we use it to improve the sample quality at each discretization. So after using this equation 19 here, that you see, this simple Euler-Maruyama, after using that to estimate graph samples, we correct the estimated graph samples. And epsilon here is just the norm of the noise. So the extra correction steps reduces the error from numerical solvers, obtaining more accurate margin distribution of graph samples. Thus, we can employ the corresponding ODE for efficient graph generation. So we can derive the probability flow ODE. So this is the probability flow ODE. It allows us to use current well-established ODE solvers to generate high-quality graphs in very few steps. So for their experiments, they use MMD, maximum mean discrepancy, and that's it. They have some experiments on enzyme, ego, small, different kinds of graph, and different models, like GraphGDP is their model. They compare it even with variational graph autoencoder that has better degree clustering, different measures for performance. So this is a visualization for community small as well as enzyme. These are enzymes. And this is the ego data set. So there is also various score function parameterization you see here. These are related works.